Okay, so we're going to continue our discussion of bipartite graphs here, but first, before we get back to that, I need one more important definition, and that's of an induced subgraph. So this is a special feature that a subgraph might have. A subgraph H, subgraph of G. So a subgraph is going to be induced if it has the property that anytime there's an edge of the original graph with ends, say, x and y, and you have x and y in the vertex set of your subgraph, then you have to have that edge. So in other words, if for an induced subgraph, you're going to have some subset of vertices that are in your subgraph, and then you have to have all of the possible edges in the original graph with all of their ends in that set. Right? So you just sort of you pick which vertices you want, and then you take all of the edges on that set. That's what it means to be induced. So subgraph H of G is induced if it has the property that every edge of the original graph with both ends in the vertex set of H is also in H. If every edge of G with both ends in the vertex set of H is also in the edge set of H, is in the edge set of H. Equivalently, induced subgraphs are precisely the subgraphs that you get by deleting vertices, but not edges. So I gave you as an operation, you start with the big graph, and I allow you to delete vertices. So if you delete some subset of vertices, then here's the vertices you're left with. Well, you'll be left with all possible edges with both ends in that set. So equivalently, H is induced if, in fact, H is exactly the subgraph you get by taking the graph G and then deleting all of the vertices that are not in H. So if you take the graph G and you delete the vertices that are not in H, then that has to be H itself. So anyway, so an induced subgraph, the way I think about it is induced by a set of vertices, right? So I give you a big graph. You're interested in making a subgraph on some subset of the vertices. With a subgraph induced on that, you take that set of vertices and all possible edges, and that's an induced subgraph. Another way of describing this is, okay, if you want to make the graph on this set of vertices, the induced subgraph on this set of vertices, we'll just delete the rest of the vertices. If you delete the rest of the vertices, when you delete those vertices, you're deleting any edge that's incident with them, so you'll be left with just all the edges on the other set. So let's just do a quick example here. It's a very easy concept. So here's graph G. The 6 vertices. Again, if I wanted to make, there's an induced subgraph with vertex set 1, 2, 6. If I want vertices 1 and 2 and 6, then you have to take all edges with their ends in that set. So this is induced. Let me draw another induced subgraph. These will be induced. subgraphs. There's one with vertices 1 and 2 and 6. I could make another with vertices 3 and 4 and 5. Oh, maybe I should 3 and 4 and 5 and 6. Those are two separate examples. Those are not meant to be the same example. I'm not sure if it's going to help to put a line in there or not. Those are two separate examples. So again, for an induced subgraph, you're taking some subset of the vertices and then all possible edges with both ends in that set. Or equivalently, you're just deleting some vertices. So if you want the induced subgraph with vertex set 1, 2, 6, well, that means you delete all the other vertices. You delete 3, 4, and 5. Now, a non-induced subgraph that means that you're going to have you'll have some subset of the vertices that are the vertices in your subgraph, but you won't have all possible edges. So if you have a subgraph that's not induced, then you're missing an edge that you could possibly have for the collection of vertices that you took. So for instance, there's a not induced subgraph with vertex set 1, 2, 6. Let me make a not induced subgraph with vertex set 3, 4, 5. 3, 4, 5, 6. I'll follow the same pattern I had before. There we are. So again, yeah, so an induced subgraph, it's a subgraph where you pick some subset of vertices that you want in your subgraph and you just take all possible edges there, or equivalently just delete some vertices that you don't want. Okay, so that's the concept of an induced subgraph. Now with that in hand, I want to return to our previous theorem. The theorem that we have about bipartite graphs is very, very nice. It's very important too. So a graph is bipartite if and only if it has no cycle of odd length, or if and only if it has no closed walk of odd length. And now, in fact, what we're going to do is really just add another condition on here. So, in fact, why don't I just... So what we're going to do now is add a fourth equivalent condition. G has no induced cycle of odd length. So what's going on here? Well, again, a subgraph is going to be induced if you've got all of the possible edges on that subgraph. So some cycles in your graph are going to be induced and some will not be. What does a cycle look like if it's induced? Well, that means that the subgraph has that cycle and nothing more. If the subgraph is, if you have a cycle that's not an induced subgraph, then that means there's some extra edges of the original graph with both ends on that cycle. So you sort of have a kind of a shortcut or a jump across that cycle, right? And so our theorem here, G is bipartite if and only if no cycle of odd length, close walk of odd length, induced cycle of odd length. There's actually kind of a hierarchy that is in a little bit of a funny order here. An induced cycle of odd length is kind of a special cycle. And if I give you a cycle, that gives you a closed walk that has only the first and last vertex repeated. So kind of I think of the induced cycle as being a really special object. A cycle is less special, and just a closed walk is even less special. It's even a more flexible object. So this so what we're doing here in a sense is kind of sharpening this. I would say that usually the main fact that we want about bipartite graphs is that a graph is bipartite if and only if it does not have an odd cycle, by which I mean cycle of odd length. But the form I'm going to give you here is just a slight strengthening of that that's sometimes very useful. So if you didn't want just any cycle of odd length, well, we can be a little bit more specific. We can prove that you're bipartite if and only if you have no induced cycle that's of odd length. So what we're going to be doing here is I'm tacking on this additional condition. Now, we've already proved that conditions 1 through 3 are equivalent. So now I'm just kind of tacking on one more. So I want to prove here that So I want to prove here that condition 4 is equivalent to 1 and 2 and 3. And again, as a reminder, we've already proved that these three guys are equivalent. And so what we're going to do, in fact, is so I need to establish that 4 is equivalent to these things, but certainly what's easy here is say 2 implies 4 is trivial, is let me say immediate. Again, I'm not hopefully I'm just being clear in what I'm saying here. This is written out in a slightly different way in the notes, but I'm writing it here a little bit more the way I'm thinking about it. I'm just thinking I'm giving you another equivalent statement to what it means to be bipartite. And I think of this as a refinement of that no odd cycle. A finer version is no induced odd cycle. Because we already know that the first 3 conditions here are equivalent, the only thing we have to do is prove that something in 1 through 3 implies 4, and 4 implies one of those earlier ones as well. So what I'm claiming here is that 2 implies 4 is quite immediate. Why is that? Well, if you have no cycle of odd length, you certainly don't have an induced cycle of odd length, right? Again, then induced is just a special type of cycle. So if you don't have a cycle of odd length, you certainly won't have an induced cycle of odd length. Now, to complete the proof here, we're going to go and do 4 implies 2. And again, I'll say here that what we want to be quick to do here is what we want to be very quick to do here is turn these things around and think about contradiction and think about contrapositive. So I have a I have a graph that by assumption now has no induced cycle of odd length. So I know that of the special kind of cycle that's induced, you won't see one of those that's of odd length. Now I want to take advantage of that to prove that in fact you do not have any cycle of odd length. But once again here, if you say contrapositive, this suddenly becomes a nicer expression where I give you something, right? So to prove 4 implies 2, the contrapositive here is not 2 implies not 4, right? So I'll just write it out again. Proof by contrapositive. So we're going to prove not 2 implies not 4. And this has exactly the same form as we had before when we were going between cycle and closed walk. So this is very, very, very similar in structure. And indeed, I really hope you're seeing a parallel here, right? Again, like if I give you a cycle, you can turn that into a closed walk of a special form that has no additional repeated vertices other than first equals last. You just pick a vertex of that cycle and walk around. So if you think about a cycle as being a kind of special kind of closed walk, then and what I'm doing now is we're talking about an induced cycle, which is a special type of cycle. So we're going to do exactly the same argument here to get between these two things. So again, now we're going by contrapositive, and now because I'm saying not 2, I'm negating 2. So 2 is the condition, no cycle of odd length. Well, negating, that's great. That means there exists a cycle of odd length, right? I'm giving you a graph that has something. It has a cycle of odd length. That's great. It's something to take a look at, something to draw. I'm giving you a cycle of odd length. I'm trying to prove now, not 4. I'm trying to prove that it has an induced cycle of odd length. So our argument here, we're going to try and show that if you have a graph that has a cycle of odd length, then it has an induced cycle of odd length. That's our argument, right? But again, the thing that we've really got going for us, what's great now is you've got something in your graph, right? It's not just any graph. It's a graph with a cycle of odd length. So here it is. I'll draw a cycle of length 7. There it is. So your graph G has a cycle of odd length. We're trying to prove that it has an induced cycle of odd length. Well, there's your cycle of odd length. If that's an induced subgraph, you're already done. Hooray. Declare victory. If it's not an induced subgraph, then what does it mean? It means that your graph has to have an additional edge with both ends in the vertex out of that cycle, right? Your graph has to have such an edge. But now look what's going on. Now we have, now you see 2 new cycles, right? We sort of have a theta shape here. So we know that the outside cycle there is odd in length. So because that outside, let's give names to these 2 vertices here. So I have a cycle C that has odd length. I'm now showing you an edge of the graph that's not on this, that has both ends in this cycle. So its ends are X and Y, but the edge is not part of the cycle. So when I toss in this edge, I now have a kind of theta shaped thing. So my original cycle has 2 different paths from X to Y, right? There are 2 different paths with ends X, Y in that original cycle. And one of them has got to have even length, and one of them has odd length, because when I sum up their lengths, I get the length of the whole cycle, which is odd. And now what happens? Well, if we take that even length path from X to Y plus this little shortcut edge, XY, you've now found another odd cycle. So what's gone on here is if I gave you an odd length cycle and it's not induced, that means there's a little edge giving you a shortcut, and then either the left side or the right side, you're going to see a new cycle in here that's going to be odd in length. And in fact, this new cycle that we get is going to be shorter. And so what I'm doing here is once again kind of talking through how we find the proof a little bit. Again, you take the statement that you're trying to prove. I'm trying to prove no induced odd cycle means no odd cycle. Well, we're going to take the contrapositive because it allows us to kind of instantiate something. Now I'm giving you a graph that has an odd cycle, and you're trying to prove something. It has an induced odd cycle. Well, that odd cycle that I gave you is a thing you can draw. There it is. There's a cycle of odd length. If it's induced, you're done. If not, there's an additional edge, and suddenly we see a shorter odd cycle. So once again, I find it cleanest to write these proofs in a kind of non-algorithmic form, in a form where I am going to I'm going to make a careful choice. So one way of writing out this proof would be writing out this argument that if you have an odd cycle and it's not induced, then you have a shorter odd cycle, and then you win, and then you repeat that. Another thing you can do is just make a careful choice. So the proof is going to be, we will choose a shortest odd cycle. So I'm going to choose a shortest odd cycle of G. And now I don't have space to write this. This proof is appearing in the notes. If I choose the shortest odd cycle, now if that cycle is not induced, if there's some edge of the graph that has both ends in the vertex of that cycle but is not itself part of the cycle, it gives you a little shortcut, and you're going to find a shorter odd cycle. So this let me give it a name. Let's choose the shortest odd cycle, C of G. The claim is C is induced. Again, the proof of this claim is just a quick contradiction. If it's not induced, there's this edge. One of those two new cycles that you form is going to be a shorter cycle of odd length. That means C is an induced odd cycle, and that means you're done. That's all there was to prove. So, right, so sort of bigger picture now, we have established a nice couple of properties about bipartite graphs. So a graph is bipartite by definition if it has a bipartition. If you can partition the vertices into two sets, left and right, so that all edges have one left end and one right end. We've proved that that's equivalent to now a few statements. I would say usually I'm going to say a graph is bipartite if and only if it has no cycle of odd length. That's the one that I view as kind of most basic and most useful. But if you want, we can refine that. We can say, in fact, no induced cycle of odd length. That's an equivalent statement. I want to say here that I've tried to emphasize a little bit in discussing these proofs how we like to kind of act in the sense that if I'm trying to prove something and I can take advantage of some assumption, even possibly by saying proof by contradiction or proof by contrapositive, if I can take advantage of an assumption that allows me to kind of draw a picture and see a little bit of structure in the graph, I'm going to jump on that. I'm going to look to do that. And a really nice thing that's happened here that I just want to point out kind of in the context of that statement is that for bipartite graphs, if I tell you that a graph is bipartite or I tell you that a graph is not bipartite, in both instances, we have a nice picture we can draw. So that's really a nice statement, right? If I tell you, hey, I'm giving you a bipartite graph, how can you take advantage of that? Well, if the graph is bipartite, there's a bipartition. There you go. Here it is. If I tell you the graph is not bipartite, how can you take advantage of that? Well, that means you've got an odd cycle, right? If the graph is not bipartite, that means you must have an odd cycle. And that's an if and only if statement. So you're taking full advantage of that assumption. So a very convenient thing about the notion of bipartite is we have a nice picture we can draw. We have a nice structure for what it means to be bipartite. We have a nice structure for what it means to not be bipartite. If you are bipartite, you have a bipartition. If you're not bipartite, you have a cycle of odd length. And if you want, you can insist that that cycle be induced. But that feature that we have a nice picture we can draw to take advantage of having the property of bipartite, and a nice picture we can draw to take advantage of the fact that the property of not being bipartite. That is very, very powerful. It's very useful, and you want to look to apply the one of these properties that is most convenient when you're doing your proofs. Okay, so that's it for this mini section on bipartite.